Okay, so I think we can start now. Well, first of all, this is Fabio. Most of you already know him. He's a PhD student here with us, with our research group, and he will give this lesson on nutritive solutions for hydroponic systems. So, Fabio.
Good morning, everyone. Nice to meet you. So we can start already with the presentation if you want.
Wait, I'm gonna find it.
Okay, so today we are going to present how to prepare a nutrient solution and what is needed to prepare a nutrient solution and how to manage it. We will have only half an hour, so we try to be as most synthetic as possible, but there are a lot of things I would like to talk about, so let's start immediately. Okay, so hydroponic nutrient solution. So first of all, now it's not working.
It's not working.
Maybe from down.
Okay, this.
Okay. So first of all, I would like to talk about the nutrients that are required for the plant growth. As some of you may aware of, there are three main elements that compose the 96% of the total biomass of a plant, which are carbon, hydrogen, and oxygen. These three elements compose the 96% of the total biomass, but they are not acquired through the nutrient solution, or better, hydrogen and oxygen are acquired from air and water. Meanwhile, carbon is acquired through the fixation of carbon dioxide, as you will know. On the other hand, we have other nutrients that are fundamental for the growth of plant, and without them, the plant would not grow or be very stunted growth. And we have we divide three different types of nutrients based on the quantity that is required from the plant. So we have macronutrients that are nitrogen, phosphorus, and potassium, that are the ones that are required in the highest quantity. Then we have the mesoelements, which are required still in a very high amount. So there is also a discussion that is going on if to include them in the macronutrients. So the mesonutrients are calcium, magnesium, and sulfur. And then we have also the micronutrients, which are supplied in very little amount, but still, even if it is a very little amount, without them, the plant would not grow. These elements are like boron, zinc, iron, copper, manganese, molybdenum, and chlorine. So what is a nutrient solution? Well, first of all, let me give the definition of a solution. That is when substances like sugar, salt, or fertilizers are dissolved in water, and the resulting liquid is called a solution. Specifically, if fertilizers are dissolved in water, then we talk about a nutrient solution. So, a nutrient solution is a carefully proportioned blend of water and minerals that are supplied in a certain precise amount with a certain ratio within the elements, which purpose is to deliver water, oxygen, and vital mineral elements derived from soluble salts, to the plant roots. So, as we said, the three main elements of a nutrient solution, let me repeat, are water, soluble salts, and oxygen. So let's see what is needed for the correct management of an hydroponic system and its nutrient solution. So what is needed is, of course, water, as we have already said. Then we need also an acid or a base that are needed to adjust the pH that we will see after. We need the fertilizers, of course, which must be minerals and not organic, because organic fertilizers cannot be used in hydroponic systems the most of the times. And then we need also a precision balance or a pipette, which are needed, of course, to quantify the amount of fertilizers that we need. But still, there is something else that we can apply in our hydroponic system, because we can increase the amount of automation and also the monitoring and the management of the system. So to increase the automation, we can use pumps. There are different types of pumps. We have air pumps, we have recirculating pumps, but we will see after. Then we need a pH meter for the measure of the pH and to be sure that there is a stability of the pH and that it is in the correct range. And then also an EC-meter for the measure of the quantity of salts that are dissolved in water. Okay, so now we talk about the nutrient solution and how it is supplied to our plants. So the nutrient solution can be provided to the plants in two ways that are active or passive. In the passive way, we can use or a floating system. So we have the plant that are, as in the image, in the upper image on the left, you see there is a floating material that is put on the nutrient solution, and the plants will grow on this floating substrate, let's say, with the roots completely submerged inside the nutrient solution. In this case, we need to be very careful because the oxygen inside the nutrient solution, if we don't move it, maybe there may be a lack of oxygen. So it's very important to, there is someone, maybe we need to accept him.
Maybe, yeah. Just one question. Can you accept the people entering in the... Perfect, thank you very much.
Sorry.
Okay. No? Yeah.
Okay.
Oh. Stop. Bye.
Okay, let's go back. So we have seen the floating passive system, and now let me see the gravity passive system. So in the gravity passive system, we have an upper tank that is put 2 meters above the ground, and by gravity, using pipes and tubes, the water is sent to the hydroponic system. On the other hand, we can use electricity, which permit us to use pumps, and resulting in a higher degree of automation of the hydroponic system, saving time and avoiding the possibility of drying the roots, because there is not the need of having an operator going to irrigate the plants one by one. So we have two different type of pumps. We have air pumps, and then we have also recirculating pumps. Si può levare così?
Sì, infatti non so come si fa, sai?
So we have...
sorry.
Oh, nice go.
Okay.
So the air pumps may be used, as we said before, in the floating system in order to increase the amount of oxygen that is dissolved inside the nutrient solution. Meanwhile, the recirculating pump are used in system like in the image on the bottom, on the left, where the pump sends directly the nutrient solution to the roots of each single plant, and then is collected back in the main tank. In these cases, it's very important to consider the power and the liters per hour that are produced by the pump, which are very important parameters that must be considered, especially in very big hydroponic systems. So let's see in details the gravity fertigation system. This system is not feasible for a large hydroponic system, but is very useful for a homemade hydroponic system, let's say, or simplified hydroponic systems. And as we said before, we have an upper tank positioned 2.5 meters above the ground, where there is a nutrient solution, and a primary PVC polyethylene pipe or polyethylene pipe is connected to the tank and brings the water directly to the hydroponic system, where smaller tubes will bring the nutrient solution directly to the plant roots. The problem of this system is that all the nutrient solution that is not uptaken by the plants will be drained in another tank that after must be replaced inside the upper tank that is 2 meters above the ground, and so very difficult to arrive to it. To avoid it, in this system, it's very important, however, to use taps in order to regulate the flux of nutrient solution that is arriving to our plants. Otherwise, all the nutrient solution would just finish in 10 minutes. To solve these problems, we can have a higher degree of automation of our fertigation system using the pumps. So here we have a very easy scheme of how it works. And you can see that we have a main tank on the left, that is where we collect our nutrient solution. That is connected through a pipe to a main pump, But there is also a filter before the pump because it's very important also for the maintenance and the management of the pump to avoid that any particle can damage the pump. And so the use of filter is fundamental in order to avoid to have the need of replacing the pump once a year because it breaks due to the absence of filters. So after the pump, the nutrient solution arrives directly to our plants, and then the nutrient solution that is not uptaken from the plant goes back into the drainage tank that we call, where there is another pump. In this scheme, there is an error because the filter of the pump below must be before the pump and not after, because the filtration is required to avoid that the pump can be clogged or can be blocked. And so the filter is not correct in this image. It should be before the tank, before the pump, sorry, inside the tank in this case. There is another type of automated fertigation system, which is even more advantageous, but cannot be applied in very large hydroponic systems. That is a combination of the automated fertigation system that we have just seen and the gravity system. So in this case, the tank is put directly below the cultivation system, and so the pump will just pump the nutrient solution inside the hydroponic system, and then when the feeding is over, the water will drain back into the reservoir below the system. So in this case, we don't need two different pumps. We need only one, and we will also use less electricity because we don't have to bring back the nutrient solution to our main tank. Okay, now let me introduce another important concept. Sorry for this. And this concept is the concept of ions. So ions are nothing else than atoms or molecules which are charged. This means that there is a loss or a gain of electrons by the atom or the molecule. And so we will talk about cations if there is a loss of an electron. And when there is a loss of an electron, there is a gain of a positive charge because you are losing an electron, which is negative, and so you become positive. On the other hand, we have anions, which gains an electron, and so they gain a negative charge and becomes negatively charged. This is very important because all the nutrients can be absorbed by the roots only if they are in ion form. Okay. So we have just seen that the nutrients are present in ion form, and so now let me talk about electrical conductivity. So the electrical conductivity is used to measure the salt concentration inside our nutrient solution, so the amount of nutrients that there is in our nutrient solution. To measure it, we use this instrument that you can see on the left, which is an conductivity meter. Which is an instrument that gives us a value that gives us a number presenting a value in microsiemens per centimeter or millisiemens per centimeter. The optimal range of electrical conductivity depends on the type of crop, the age of the plant, and the phenological stage, but also from the environmental conditions, and we will see after why. The units of measurements is very important to consider which units of measurement we are using. Otherwise, we can have problems in the reading of the values. And also the importance of the correct ratio between the elements is very important. Otherwise, the uptake of an element may be reduced due to the presence of a high amount of another element. Another thing to consider is the water that we are using, because there is a great difference between tap water and rainwater, and we will see why. So here is a tab where the best range of electroconductivity for each kind of crop is presented. And you can see that there is a great difference between plants which produce fruits, like peppers, tomatoes, strawberries, in respect to the ones that produce from leafy vegetables, like basil, mint. You can see that leafy vegetables require very low electroconductivity. Meanwhile, fruiting plant require very high amount of minerals. On the bottom, instead, you can see the unit of measurement conversion, which is very important. And you can see that 1 gram per liter of a salt corresponds to 1000 ppm, which is part per million. Another important unit of measurement, which is the main unit of measurement used by the electroconductivity meter, is the decisiemens per meter, or the millisiemens per centimeter, or the microsiemens per centimeter. You can see that 1 decisiemens corresponds to 1 millisiemens per centimeter. Meanwhile, 1 millisiemens per centimeter corresponds to 1000 microsiemens per centimeter. This is very important. Okay, so we have just seen the amount of salts that are dissolved in our nutrient solution and how to measure it, how to manage it. Let we see now how to measure their availability, because the availability of the nutrient is dependent from the pH, which measures the acidity or the alkalinity of our nutrient solution. So the pH, usually the rainwater has got a slightly acidic pH, so let's say 6.5. This is very good for us, because you can see that the optimal range is between 5.2 and 6.5. But there is a problem, because when we are going to add our minerals to our nutrient solution to put the nutrients inside the nutrient solution, the pH can change, because as we said before, our salts are composed by ions, and the ions are charged positively or negatively, and this will increase or decrease the pH. Okay, so the pH can be measured also with the use of pH meter or the litmus test. Actually, the litmus test is not very suggested, because it's not precise, and also you have to continue to buy it. Meanwhile, the pH meter, you buy it once and then you have only to calibrate it. You need to remember to calibrate it very often, more often than the EC meter, because it's very delicate. And it's very important also to always remember to close the cap of the pH meter. The pH can go from 0 to 14. I forgot to say it before. Okay. On the left, you can see in the image the availability of each single mineral, of each single nutrient, and you can see that there is a great difference between each nutrient. So, for example, iron is very available at acidic pH. Meanwhile, for example, phosphorus, you can see, has got a strange behavior, increasing and decreasing its availability. Okay, so how to increase the nutrient availability? So how to change the pH of our nutrient solution? Well, to do so, we need to use an acid in order to increase the acidity, or a base in order to increase the alkalinity. So we prepare our nutrient solution, and then we measure the pH. We see that the pH is 6.75, which is too high for us. Then we need to decrease it. We want to bring it up to 5.5, for example. How to do so? Well, basically, we collect 1 liter of our nutrient solution. We check the pH of the water. And if the pH, of course, will be still 6.75, then we start to apply a little bit of acid, always measuring the amount, so with a balance or a pipette if it is liquid. And we see, applying a little amount of acid, how much it will, the pH will decrease. We repeat the operation if the pH is not low enough, and we continue to repeat it until we don't reach 5.5. When we are fine, we measure the amount of acid that we needed to dissolve into 1 liter of nutrient solution. And so using the formula that you can find on the bottom, you can see that you have just to multiply the amount of grams of acid that you used for 1 liter for the total amount of liters that you have in your tank. Okay. And always remember to add the acid to the water and not the opposite, because it's very dangerous. The acid is very corrosive, and if you put the water on the acid, it may go on your leg or somewhere, and it's very dangerous. So be very careful. Okay, so water salinity. The water salinity is very important because the water quality that we use for the preparation of our nutrient solution will also affect the nutrient uptake from our plants. So let we start about, let we look to the right part of the slide. Let we talk about the difference between tap water and rainwater. So tap water usually has got a very high pH, depending, of course, on the area where you're living and the type of soil and rocks that you have, and also a very high electroconductivity, because there are a lot of salts that are dissolved in it. So the correction of pH and dilution with rainwater are the first step, which are very important, because we need to bring the pH to neutral, so to a value of 7. On the other hand, the rainwater has got a slightly acidic pH and a very low electroconductivity. And so, if we are using rainwater, the integration of calcium and magnesium may be required for some crops. To do so, we can dilute the rainwater with some tap water, which will contain for sure some calcium. Otherwise, we can buy calcium and magnesium and integrating them as salts. Another important fact is that the water with an electroconductivity higher of 1000 microsiemens per centimeter is suitable for hydroponic cultivation. Sorry, lower than 1000 microsiemens. If it is higher than 1000, it's not suitable. Also because we have seen before, the maximum electroconductivity is 2000, 2200. This is a very high electroconductivity that is used only for some crops like tomatoes. But of course, if we are starting, there is a great difference of nutrient content in our nutrient solution if the electroconductivity of our water that we were using were 200 or were 1000. There is a great difference because from 200 to 1000, there is 800 microsiemens per centimeter that could have been nutrients. Meanwhile, they are all salts that cannot be used by the plant. Okay. So let's move to the monitoring and management of our hydroponic solution. So first of all, we need always to check daily, even more times per day, the electroconductivity and the pH of our nutrient solution. So we go to our tank, we measure it, and we observe the behavior during time of our electroconductivity. If we see that our electroconductivity tends to increase in time, this means that plants are absorbing more water than the salts, the nutrients inside the nutrient solution. This means that we are using a too high electroconductivity. So in this case, we need to increase the amount of water, decreasing the electroconductivity, and so we can just dilute our nutrient solution, bringing it to a lower electroconductivity. On the other hand, if we see that the electroconductivity during time decreases, this means that we are using a too low electroconductivity and that plants are absorbing more nutrients than water. In this case, instead of diluting it with water, we need to dissolve even more salts inside our nutrient solution. Always remember to use the correct ratio between the elements. Okay, so remember also that if you apply fertilizers to your nutrient solution, After you do that, you have always to check the pH because, as we said before, the nutrients will change the pH of our nutrient solution. And so we need to restore the optimal pH conditions. Another important factor is that the electroconductivity is dependent on temperature. So if our nutrient solution is very hot, the value of electroconductivity may be increased in respect to the one that we measure during the night when it's colder, for example. This is normal. So we suggest to try to maintain the nutrient solution temperature between 18 and 28 degrees Celsius. Another factor, which I want to underline because it's very important, is that it's almost impossible to realize a perfect nutrient solution that is stable in time and that has got exactly what the plants need. Also because the plant, during their growth, changes their requirements. And so it may happen that there is an accumulation of unused nutrients inside the nutrient solution, or the opposite, a depletion of some nutrients which are completely missing. Another fact is that plants, in order to absorb nutrients, are releasing inside the nutrient solution protons and carboxylate excretion by the roots. And this not only increases the pH, but changes also the pH, because protons are positively charged, and so they will increase the pH. So this may be another factor for which the pH of your hydroponic system is not stable, because you have a lot of roots and not enough nutrient solution. In order to avoid all these problems, my suggestion is that you have to change completely the nutrient solution inside the tank once a week, at least once every 2 weeks. This because you will not have the problem of accumulation or depletion of nutrients, and also to clean very well the tank where there may be the formation of microorganisms and algae. Of course, when you have to do it, try to finish as much as possible the nutrient solution, because you cannot discard or for other patches and things like this. On the right image, you can observe the Mulder chart, is called, which tell us which are the main antagonisms and synergism between different elements. Because the presence of an element in a ratio which is not the correct ratio can also decrease the absorption of other nutrients. For example, if we have too much phosphorus, you see that phosphorus has got a lot of antagonists, like calcium, potassium, iron, zinc. And if we have too much phosphorus, we can also have deficiencies of those nutrients, not because they're not present or because the pH is not the right one, but because we have too much phosphorus, which accumulated inside the nutrient solution, and it can also react with calcium and precipitate, creating salts that will not make the nutrients available. So we were talking about microorganisms. In fact, it may happen that a biofilm,
5 minutes.
A biofilm forms in the tank, and so we need to make sure to avoid the formation of microorganisms. So we should try to dry up all the surfaces of our hydroponic system. The oxygen is always important to check the pumps that are working and mixing the nutrient solution. The presence of algae, the same if there is the accumulation of water in some trays or parts of your hydroponic systems, there may be the formation of algae if the sun is arriving. Also in your tank, you need to be sure that there is complete darkness, otherwise also there will be algae formation. Also the substrate can form molds and algae, and so it's very important to have irrigation cycles that permit to the upper part of the substrate, if you're using it, to dry up. Another very important problem is the salt deposits, which may occur in time because the minerals, when the water dries, will accumulate on the surface of your pipes, and they can also rise to clog completely the system. To avoid that, we need to periodically clean an irrigation system, and to do so, it's very easy. You need only to remove your nutrient solution. So when the plants are not present in the hydroponic system, so every time you finish your growing cycle, you remove your nutrient solution, you remove the plant, and you substitute the nutrient solution with an acidic solution of a pH of maximum 2, so a very acid solution. You turn on the pump, you let it run for 1 hour, and then you remove the acidic solution, and you will see that all the salts will be the most of the salts will be disappeared. Do you have the time to talk also about filtration?
Very quickly, yeah, the filtration.
Okay, so we were saying before that it's very important to use filters in order to avoid the clogging of the pumps. In particular, of course, if you're using an open cycle, usually you don't have this problem because all the water that passes through the substrate is discarded. On the other hand, if you're using an open cycle, you will know that is not environmentally friendly because you are discarding a lot of nutrients which will pollute the soil and the rivers. So we suggest to use closed cycle. The drainage of our nutrients of our hydroponic system is collected and reused, so is reintegrated in the main tank. Before doing it, we need to filtrate it because the pumps are very susceptible to the presence of particles. And in order to prolong the life of our pumps, which is a great investment, and you want to maintain it as healthy as possible, you want to use filters. There are two main types of filters you can use that are the disc filter and the mesh filter. Are very similar. Are very similar type of filters, but they use different type of filtration systems. So the disc filter has got a lot of discs, one on top of the other, with small holes on the side, and the nutrient solution will pass through those small holes, and then is collected back in the pipeline. For the mesh filter, instead, we have a mesh, which we very easily will collect all the particles and biofilms, and you have just to open it once a day and clean it with water. Okay, so now there should be also an introduction to deficiencies and toxicities, and I also would like to talk to you about all the deficiencies that may occur, but we don't have time. So if you want, the next time we can see, or maybe we can organize a private room. We can talk about deficiencies, but also how to calculate a nutrient solution using the empirical approach or the use of software, which are very useful and very easy to use. So thank you very much for your attention. Here is my email if any one of you needs to contact me. And thank you again.
Okay. So let's stop the sharing. Correct. Okay. Do you have any question concerning the presentation? Well, just one thing, as Fabio said, we had a very important part actually on deficiencies, which I think it's actually very useful. So we didn't plan to have a second part of the seminar, but I think it may be very useful to have this second part on deficiencies and also a short introduction on the use of softwares for nutrient solutions preparations. So if you agree, we can add this presentation the next week and start 30 minutes more and a quick introduction on that. Anyway, we will share all the slides. I think we can already share everything, so you can eventually study everything in advance. Okay, so I think there is a, yeah, okay. There is a question from Amer. Amer, please.
Hello, everyone.
Hello.
Hi, thank you for the presentation. My question is regarding the root system in the hydroponic system. You said something about microorganisms and they're making biofilm, and then we need microbes for the roots, for the ribosome, like they are a need. Have you noticed there's a conflict between biofilm and roots, and can you elaborate on that?
Yeah. So if I got the right question, you're asking if microorganisms are a problem for the roots, right?
I mean, the roots need them, and also at the same time they make a biofilm.
So actually, in hydroponic system, microorganisms usually are not wanted because in the hydroponic system, since we have everything very clean, there may be the proliferation also of bad microorganisms. So usually what we do is to try to create an environment that is not suitable for the proliferation of bad organisms. And to do so, we need or to increase the amount of oxygenation of our nutrient solution, or to increase the movement, the flow of our nutrient solution that do not permit to the microorganisms to create the biofilm, which is that sort of mucilaginous, that moldy, I don't know how to call it.
Biofilm simply all the waste of the microorganism.
Yeah, actually, the microorganisms are living inside the biofilm, and if there is the biofilm, there is the creation of even more suitable conditions for bad microorganisms. So we need absolutely to avoid the creation of biofilms.
And algae also.
And also algae, of course.
And of course, in this case, you can use, you can cover and avoid light penetration to avoid the formation of algae. That's why normally everything is covered, all the tubes and everything. I mean, not the tubes, the slopes.
Pipes.
Yeah, pipes, exactly.
Did I answer?
But may I ask too?
Yeah.
Maybe could it be that the situation is different from hydroponics to an aquaponic systems, because Amar is with the background more, I think, on aquaponics, and I remember our systems, for instance, in Ghana. You remember, Elisa, everything in the open and so on. Could that make a difference regarding the microorganisms? With regard to whether they are harmful or not?
Of course. But there is a great difference between hydroponics and aquaponics. Because in hydroponics, we are using mineral salts. Meanwhile, in aquaponics, we are using organic matter. That is converted into mineral salts from the microorganisms. But in this case, we are providing a safe place because in the aquaponic systems, we always have a filtration system. And this is the home, the house of the microorganisms, we can say. So we create a perfect environment for good microorganisms that is inside the filter. And then from there, where all the filters, where all the microorganisms will work and convert the organic matter into mineral salts, then the nutrient solution with the mineral salts is supplied to our plants. Of course, there will be still some organic matter, which can produce the proliferation of bad microorganisms, but these usually occur in conditions where there is a lack of oxygen. So if we have oxygen, usually we have only good bacteria.
May I ask a second question?
Of course.
Because you were talking about cleaning the tank and cleaning the pipes and so on a regular basis and using acid, for instance, for the tank. And so I was wondering what is going to happen with the, how do you say, the dilution, the
acid.
Huh? Yeah, with the acid
solution.
Do you neutralize it before you put it into the open, or could you use it for a conventional garden if you somehow dilute it more? I mean, because one aspect of our project is always also to reduce the pressure on the environment.
Mm-hmm.
And of course, putting acid into the open is maybe
Of
not
course.
so optimal for the environment.
Yeah, sorry for due to the short time, I couldn't.
Yeah, sure. That's why I ask.
Yeah, no, very nice question. So first of all, you need to prepare not a large amount of acid solution. You need to prepare only the amount that is needed to run it inside the hydroponic system.
Up to
when
the
you finish
weld,
to
maybe
use it,
to
sorry?
the weld, up to the weld. You know the turn.
La valvola.
Sorry.
Diceva se fino alla valvola. But just a small amount, it's fine, and you can pump it with the pump.
Ah, okay.
Yeah.
So exactly. So the amount that completely fills all the pipes and do not leave the pump running without nutrient solution. Otherwise, the pumps will break.
Destroyed. Yeah.
But the important thing, as you were saying, is that after you finish to clean the system, you collect it, you increase again the pH, as you said, exactly. But of course, also these you need to use salts. You need to use very strong bases to increase the pH, and as stronger it is the base, as lower is the amount of the base needed, which is even better because you're using less minerals, less salts. After doing so, you can use again this water for irrigation, remembering because when the acid enters in contact with the salts, with the minerals that are deposited on the deposit of the pipes, they will dissolve it and make it again available to the plants. This is good, but not so much, because if we are preparing again a nutrient solution with those salts present in the nutrients in the water, then the balance between the ratio between the nutrients will change. So it's not very suitable for an hydroponic system. So it's better to use it to irrigate a garden or another patch of vegetables. So,
outside the system.
Exactly. However, you can also discard it if the pH is fine, because the salts that are inside are not dangerous. So you can also discard it, but it's not suggested, of course. So it's better to use it for other purposes. You can also use it to clean your car, to clean the greenhouse. You can use it for whatever you want.
Okay, thank you.
Thanks to you for the question. Anyone else?
One comment.
Yeah, I have a comment. Usually, when you use a dosing pump, yeah?
Sorry?
Dosing pump. You use a dosing pump, just like a pulsing. It's not a direct addition, I guess.
Ok, il sistema di dosaggio degli elementi nutritivi, credo.
So you're talking about the dilution of minerals inside the nutrient solution?
When you add the solution just to play with the pH, usually you use like a dosing pump, which is pulsing chemicals, not steady flowing to the tanks. This is you make sure that you don't have, let's say, a huge portion of acid or base reach to the tank, and this is you control it more, the amount that you added with the dosing pump, using the pulse system. You add like a small amount.
Okay. So this is a very high-tech system. Yes, I was not understanding. Now I got it. Yes, of course, this is the best option, because you have a system that is automatically reading the pH of the water, of the nutrient solution, sorry, and it will dilute using dosing pumps, which are very small pumps that can measure the amount of solution that they are dissolving in the other system. In order to have always the best pH, because it will continue to measure it and adjust it to the correct ratio, and also you avoid very high concentration of acid that can damage the roots and also kill the plants. Thank you, Mariana. Is it right what you were saying?
Yeah. I just wanted to say that we don't need a huge amount of acids or base to get to the system, then we lose everything. So we
Exactly.
add dosing, like pulsing, and then we stop, then we take a measurement, and then we do again and again.
Yeah, great.
Yeah, but always keep in mind the scaling of our systems, because AMER probably what you are, as we heard, that's more a high-tech solution. And if, for instance, in Morocco, farmers are capable of using some such systems, it's wonderful, but maybe not everywhere. And I think what we saw now was also were also ideas for lower tech systems. And my comment is, Elisa, you always start out by saying it's not complicated, and then I'm listening, and in the end, I think it is complicated.
It
and
looks
not so trivial.
Once you do it, it's
Yeah.
not that complicated.
It's easier to do it than to
Okay.
explain it, let's say.
And of
Thank
course,
you very much.
Yeah, and of course, as Fabio showed, there are really many technological levels to perform hydroponics. So AMER was citing a very high-tech system, everything automatized, but there are also systems that can recycle. We've said that many times, can use recycled materials. You saw it with the PET bottles and whatever. A more higher system with pumps and let's say a more sophisticated substrate. So there is really a wide range, and as always, it really depends on the purpose of the cultivation and on the economic amount for the investment, of course.
Okay, so if we can continue with your presentation next week, that would be wonderful.
Yeah, of course.
Yeah, I think we are a bit out of time now, so maybe we should move, and if there are other questions, we can go, we can have it tomorrow. Maybe again, we should move in the other room. So sorry if we are a bit late. Okay, see you in the other room then.